Morning, and
Good
I have a
morning.
question.
Yeah, good morning, dear students. Yeah, let's start from a question, of course.
So it's not about the lesson we have on Dale. It is written that we had a practical lesson 8 on April 11th, but there wasn't a lesson.
Okay, let me correct the date. It was just
Thank you.
a mistake. Uh, okay, I will do it after the lesson. Yeah, I just need to correct date and that's it.
Okay, thanks.
Yeah, it should have been. Stop. Uh, 11 April. Yeah, the third group. Yeah, we'll correct it. Don't worry about it. So, uh, actually, that's not critical. More questions? Okay, if no questions, let's start the practical lesson itself. Let me share my screen. So, the previous week we had practical lesson 9 that was about double integral in uh, a rectangular coordinate system, and today we are continuing calculation double integrals, but in a polar coordinate system. So it is some kind of uh, variable substitution. So when do we use polar coordinates? Actually, sometimes we have some, when integrating, we have the region of integration that is a round or ellipse or segment, sector of the round or ellipse, maybe some concentric circles uh, so that form the region. So just imagine, so we have to integrate so something like this. So so one of the bound of integration looks like this. So a lot of square roots, and it's quite inconvenient, and different coefficients. So transferring to polar coordinates simplifies this task by the following formulas: x equals a rho, uh, a rho cosine over phi, and then y equals um, a rho sine over phi. So, okay, sorry. So with using these formulas, we can transfer to polar coordinates. I don't know why it behaves in such a way. Yeah. So now let's begin. First of all, we will just go to polar coordinates in a double integral with that has the following region. So it is bounded by a circle. Let's do it. Actually, it is not. So we don't know what is the function. So what is the integrand? It doesn't matter us for now. Just uh, just a function. We just need to go to power in coordinates and define the um, uh, limits of integration. So first of all, let's plot this region. The region is bounded by this circle that has the center not in polar coordinates. So First of all, yeah, we have to extract the perfect square. It will be a good idea. So x square minus 2x plus 1 minus 1 plus y square equals 0. So when I collapse it, so we write in a compact way, x minus 1 square plus y square equals 1. So we have around, so it is the equation of the circle with with radius 1 and coordinates of the center are 1 and 0. So received. And now let's do the following stuff. Let's uh, swap let's substitute the variable. So we need to, so with using these formulas, we will uh, express our region of integration with this, so in polar coordinates. So rho square and cosine square of phi plus rho square sine of square phi and equals 2 rho cosine of phi. So now we can simplify a little bit. So we will receive rho square in the left part. And now we will express, so rho will be equal here. Yeah, so first of all, yeah, let's write, yeah, so just divided by rho. So rho equals 2 cosine of phi. So actually, this is the uh, so how our region of integration is described. Yeah, by the way, what is rho? Rho is a radius, which means the distance between, so radius of distance between this the beginning of coordinates and yeah, and some curve, so pointed at the curve. So now let's describe the region of integration. So how changes phi? Phi is an angle, so between x-axis and any, so such angle between x-axis and uh, so this or any point. So how phi changes? As we can see from the plot, so which you like more. So phi actually changes from so it changes from p over from minus p over 2 to p over 2. Oh. So these are limits of integration by phi. And what about rho? So actually, as we can see from the graph, so the least value of rho is 0. So 0 distance from the beginning of coordinates. And the greatest is, so the upper limit is 2 cosine of phi. So now let's rewrite the integral. So from minus p over 2 to p over 2 d phi. And then from 0 to 2 cosine over phi. Now let's substitute. So f depends on rho cosine of phi and rho sine of phi. And be attentive, don't forget to multiply by a Jacobian over the transformation. So it equals rho in polar coordinates. So be attentive with it. Don't lose it because in this case you will make mistakes. You will receive the wrong result. So this is our integral in polar coordinates. Any questions about this exercise? Okay, I guess that no questions. And actually we have the second task is analogical. So let's go to it. So to A. So we have the following region of integration. So it is bounded by circles, by the following circles and straight lines. So let's plot this region first of all. So here I will just change it to 4x. It will be changed to 8x. So how this region looks like. Then two straight lines. So y equals x and y equals 2x. And actually, this is the region of integration. Well, we can look at it into so in my materials. So here it is. So here is the region of integration. So this circles, straight lines. So first of all, let's do the following stuff. So we need to firstly to transfer to polar coordinates in different in these curves. So let's substitute variables in these equations, and then we will understand what to do next. So the first straight line. So let's again do the substitution. So rho square cosine square of phi plus rho square sine square of phi equals 4 rho cosine of phi. So now we will simplify it. So rho square equals 4 rho cosine of phi. Then rho equals 4 cosine of phi. Now let's do the analogical stuff to the greater circle. So 8x. And here let's be attentive. So don't forget to change everything. So 8 here and 8 here. So actually we just received how rho changes. So it changes from 4 cosine of phi to 8 cosine of phi. So it is the bounds of integration by variable rho. And now let's define limits for phi. So again, doing the analogical stuff. So y equals x, and again we do the following substitution. So rho sine of phi equals a rho cosine of phi. So we can eliminate rho, and it means that sine of phi equals cosine of phi. Then, what does it mean? That tangents phi equals 1. So it means that phi equals p over 4. Then analogically to y equals x, y equals 2x, so we do the same things, but don't forget about coefficient. So 2 cosines of phi. Yeah, we can easily divide by rho because it's not 0. Then yeah, tangents of phi equals 2. And it is not a table value, so phi equals arctangents over 2. Yeah, let me check here. It is not a table value, so it is arctangents of 2. So we found all limits of integration. So let's rewrite the integral. It will be the following. So from p over 4 to arctangents of 2. So phi changes. And rho changes from 4 cosine of phi to 8 cosines of phi. And again, substituting our function that we don't know. And also don't forget to multiply by rho. Don't lose it. Be attentive. So this is the final answer. Any questions about this exercise? Okay, I guess that no questions. So for now, we will skip exercise D. So part D, actually, part B, actually it is, yeah. So analogically, so you will do it in analogical manner, but something is, uh, so something works in another way. So it will be your home task. Then now we, yeah, again, so converting given integrals to polar coordinates. So here we have already repeated integrals, so we need to understand the region of integration from the integral itself. So we don't have equations. So 3a. So integral, so the following integral will be, so x equals from 0 to r, and y changes from 0 to square root of r square minus x square. So the following integrand. And now again, so we need to Yeah, we need to substitute. Yeah, well, okay. First of all, let's plot this region. So, y equals the square root of r square minus x square. So this is the following. Yeah, and also x greater or equal than r. And yeah, and it is great. So x is between 0 and r. So this is such a quarter of the round. So now we can understand the regional integration. So from this plot, we already see that phi is changed from 0 to phi. So from 0 to uh, p over 2. So how it is changed? Then, what about rho? Again, we see that it is changed from 0 to r. So the same distance everywhere. So described the regional integration in polar coordinates. So now we can rewrite this integral. So now from 0 to 2p d phi, and from 0 to r, so rho cos f from rho cosine of phi and f from rho sine of phi multiplied by rho d rho. And that's it. So we adjusted limits of integration. So we transferred to polar coordinates. Any questions about this exercise? Okay, I guess that no questions. Yeah, also, what can we say about this? Yeah, so this exercise is analogical. But let we see if we have time for it. Actually, I guess that we have time for this exercise. So, so for part B, so let's uh, complete it as well. So let's do. So we have other uh, limits of integration. So y changes from r over 2 to 2r, and x changes from 0 to 2ry minus y square. Now let's plot this region, first of all. So x equals, yeah, let's plot this square root. So 2ry minus y square. And let's add slider for r. So we see the region. So we start seeing the region. And also we know that x changes from, oh, stop, y changes from r over 2 to r. Yeah, so different order of integration. So So we have such a segment of the, okay, yeah, and also x, oh, stop, oh no. Yeah, by the way, and x is, yeah, x equals, so is less or equals, and also x is greater than 0. So we have such a segment of the round, so it's more interesting task. And now let's see what can we do here. So the upper limit, so the following. So let's substitute r cosine of phi and rho sine of phi. Also, I can move out of brackets rho sine of phi. So 2r minus rho sine of phi. And what else? We know that, yeah, actually, yeah, so we just substitute limits of integration. So it is double inequality. So rho cosine of phi is between these values. And rho sine of phi between these values. So r over 2 and 2r. So how we will receive new limits of integration. So if yeah, so if rho cosine of phi equals 0, so rho is just yeah, well, rho cannot be equal 0 in this case, by the way. But let's check let's check this equation. So yeah, let's solve this equation first of all. So let's raise it to the square. So rho square cosine square of phi. Yeah, and actually, I don't think that it was a good idea to expand to factorize. So we could just expand brackets. So raised to the power. And now let's simplify everything that we can simplify. So we can move this stuff to the right part, and we receive that we receive the following. So now let's simplify. So we have rho square in the left part, and in the right 2r rho sine of phi. Now let's divide by rho. And we have 2r sine of phi. It is the upper limit of integration by rho. Then, yeah, so received it. And now let's check also this inequality. So rho sine of phi. Okay, if it equals r over 2, so then rho equals the r over 2 sine of phi. And what about this part? Well, actually, the same stuff, but here is 2r over sine of phi. Yeah, rho equals 2r over sine of phi. Okay. And now let's see what we actually have here. Yeah, let's also build some polar curves. So rho equals 2r by sine of theta. Let it be. Yeah, so this limit and this limit is the following. Yeah, so actually we found these bounds. And then what about so r equals 2 rho sine of phi to r sine of phi. So the following. So from this graph, we can see that rho changes from r sine of so from this value to this value. So found it. Yeah, and phi actually changes from 0 to p over 2. And now let's rewrite the integral. So from 0 to p over 2 d phi. And for rho, more interesting case. So limits are the following. Stop. 2r sine phi. So it's done. Any questions about this exercise? Okay, I guess that no questions. So let's move to the next exercise. So now we already will calculate double integrals in polar coordinate system. Of course, first of all, we need to convert it to polar coordinates, and after that, only calculate, of course. So the integral is the following. So square root of 4 minus x square minus y square dx dy. So it equals yeah. So we don't know what it to which value it equals now. Actually, what do we have? So we have the So the D is a circle over, so is bounded by a circle of radius r at the center of the origin. So x squared plus 2 square is less than 4, greater or less than 4. So actually, I don't know if we really need plot, but let's do it. So such round. So how can it be described? So yeah, so no more additional information. So it means that phi is changed from 0 to 2p. So the full so it makes full circle. uh, 2 p, and rho changes from 0 to 2. So absolutely simple case. For now, so if we calculate in okay, let's change this function also. So this expression will be the following. So 4 minus rho square cosine square of phi minus rho square sine square of phi. And if we simplify, we will receive 4 minus rho square. So the integral will be the following. So from 0 to 2p d phi, and integral from 0 to 2, 4 minus rho, multiplied also by rho, don't forget it, and d rho. So we received the following integral. So let's calculate it. By the way, we see that the limits of integration don't depend on each other, and also the integrand contains only one variable, rho. So we can rewrite it as a product of two integrals, two independent integrals. So this integral is multiplied by this integral, and calculate each of them separately. So this first actually will be equal to p. So let's not waste our time. So it is quite simple. So 2p by this integral. And now let's continue calculating. So here we can use the differential entry technique. So rho is actually the, so looks like differential this expression under the square root. So minus 2, so 2p multiplied by yeah, this integral, and now let's change it. So differential over this stuff, but also we don't have, so we have not to break the equality, so it will be multiplied by minus 1 over 2. So now everything is correct. So let's yeah, let's simplify also this stuff. So it will be minus p. And now integrating. So minus 2 p over 3, and this square root multiplied, so increasing the power, and now substitutions from 2 to 0. So now when I substitute 2, I receive 0. We can see it. So minus 2p over 3 multiplied by minus 4 by 2. So the final answer is so 16p over 3. And that's it. Any questions about this exercise?
Sorry, I've got a question. When
Yes.
can we uh, rewrite the integral as the product? You
Uh,
said we use the product here. Yeah.
yeah. So actually, when two variables don't so when two variables don't depend on each other. So here we have constant limits of integration without variable phi, and also here we have only variable rho. Actually, if it so if we had phi so as add and so for example 4 plus phi and so on, it would be impossible to transfer to product of integrals. But if for example phi is multiplied, so we can move it to this integral and just yeah, so rewrite as a product. So when actually when we can separate the variables, we can write as two. So we can rewrite this integral as a product of two independent integrals. So have I answered your question?
Yeah, you've answered. Thank you.
More questions? Okay, if you have no questions, let's have a break for now for 5 minutes, and then we will continue calculating double integrals in polar coordinates. Okay, let's continue. So now we'll have another integral. So for b, now let's calculate the following integral. So we don't have explicit description of the region, but we can find it from the limits of integration in this integral. So x is from r to 0, and y from 0 to square root of r square minus x square. And the integral is the following. So such logarithm 1 plus r and x square root of x square plus y square, and divided by this square root dy. So of course, calculating this integral in rectangular coordinates, it's not really convenient, as we can see from this expression, but transferring to polar coordinates will simplify our task. So let's first of all plot the region. So y is greater than less or equals than square root of r square minus x square. And also we take into the consideration that x is between minus r and 0. So and also y is greater than 0. So we have such quarter of the round, so we can easily describe the region of integration. So what does it mean? In this case, so phi is from p over 2 from p over 2 to p. And what about rho? Rho is from 0 to r. So found limits of integration. And now what about these expressions? So now let's substitute new values. So what we will receive? So rho, rho square cosine square of phi and rho sine rho square sine square of phi. So if we simplify it, we will receive expression 1 logarithm of 1 plus rho. And this expression will be equal to rho. So now we can move to polar coordinates, and we will see how this integrand will be simplified. So dp and from 0 to r. So what we will have here? So logarithm of 1 plus rho divided by rho, and also it is multiplied by rho. And we see that this integral is really slightly simplified that it was before. So that's why polar coordinates are so useful for us, so important. So just compare this and this. So integrate just logarithm is instead of many square roots. And also we see that we have so here we also can write it as the product of independent integrals. And actually this integral will be equal p over 2. And now let's remember integration by parts formula. So u equals logarithm of 1 plus rho, du equals d rho divided by 1 plus rho. Then dv equals d rho. So v equals rho. So p over 2 multiplied by the following stuff. So rho multiplied by this logarithm. And with the substitutions from 1 to r, from 0 to r, and minus this expression. Yeah, so the following expression will be, let me copy and paste, and after that correct. So the following expression. So here what do we have? So r plus logarithm of 1 plus rho. Yeah, let's rewrite it. So if I substitute 0, it will turn to 0. But if I substitute r, I have the following expression. And let's also extract integer part from this integral. So 1 plus this stuff and minus 1. Yeah, by the way, now let's calculate this integral I1 separately. So, yeah, and remove this stuff. So here what I have, so 1 minus, yeah, so minus 1 minus rho, so the following integral will be received. And now let's integrate. So what we will have here, so it will be a rho and minus logarithm of 1 plus rho. So yeah, I don't use module here because we know that these values are, so the argument of the logarithm in this case is positive. So r minus logarithm of 1 plus rho and minus 0. So we received this value. So now calculating the final integral with substituting what we received. So minus r plus 1 plus r. And actually this is the final answer. Now let we not expand the brackets. It really doesn't make sense for now. So this is the final answer, and let's move to other integrals. Maybe you have some questions about this exercise. Okay, I guess that no questions. So let's move to the next exercise. Exercise 5. We have a double integral in so where the region is bounded by ellipse. So let me first of all write down the integral. Again, it looks really complicated, yeah, and if we try to integrate it, to calculate the integral directly in a rectangular coordinate system, of course, it would be difficult. Even sometimes it is not always possible. And the region of integration is bounded by ellipse. So let me remind you how ellipse. So yeah, actually, it doesn't make really sense to plot ellipse. So everything that is inside the ellipse. So this is the region of integration. So in such case, we will use the generic polar coordinates with this formula. So how do they change? X equals A r cosine of phi and y equals B r cosine of phi. And the Jacobian of the transition equals A B rho. So be attentive when calculate integrals in so when you use generic polar coordinates that these multipliers appear. So first of all, let's decide with bounds of integration. Actually, bounds of integration are the following. So phi is so obviously from 0 to 2p. And if I substitute this, so yeah, now let's substitute values of, so let's substitute this coordinates. So this equation, so let's substitute generic polar coordinates into this equation. And let's see what we will receive. So plus analogical stuff with y. So b square by rho square by sine square of phi equals 1. Now let's simplify it. So first of all, canceling a square and b square. So we have that rho square equals 1. So it means that rho is from so has values from 0 to 1. So now we can transfer to generic polar coordinates. So from 0 to 1, and now let's change this, let's modify these values. So just substitute, copy and paste. So D Oh, damn it. Oh, D-row. Okay, so now let's simplify. So yeah, again, I will receive the following stuff. So minus and and my mistake, I forgot to multiply it by Jacobian, and it is a bad idea to forget it. But now everything is okay. So 1 minus rho square under the square root. And now we can integrate. Again, let's rewrite it as the product of two independent integrals. This integral by phi obviously will be equal to p. Yeah, and AB. I forgot AB here. So I told you not to make mistakes, but made a mistake. So now let's move A and B out of the integral. And now we will use differential entry technique. So what we have here, so minus 1 over 2, and differential over this expression, and rho will be erased. So AB, so minus AB by P, and we will receive the following antiderivative. So from 0 to 1. So if I substitute 1, I receive just 0 here, and if I substitute 0, I will receive 1, but we also subtract 1, so the final answer will be ABP. So we calculated the integral. Any questions about this exercise? Is everything clear? If so, let's move to the next exercise. So now, so the integrals just for integrals are useless, but actually, 2 over 3. Damn it, I forgot about this multiplier, 2 over 3. Okay, so let's correct it a little bit. So 2 over 3 and 2 over 3 here. So now everything is right. Okay, and now let's use, so let's apply the integral for calculating the area. So we have the following figure that is bounded by the following lines. So lines are already given. Oh, I cannot copy and paste to math type everything. Okay. So control, yeah, so R equals to cosine of phi, and R equals 4 cosines of phi. So actually, everything is, so we have everything that we need. Also, yeah, it is good idea to plot the region. So as we can see, so it is bounded by two circles in a following way. So how can we describe the region of integration? So phi is between p over 2, between minus p over 2 and p over 2. And rho just between these values. So the actually area will be calculated by this integral, so we just integrate 1, but when we transfer to polar coordinates, don't forget about this stuff. Yeah, so don't forget about multiplying by Jacobian. So from 2 cosine of phi to 4 cosine of phi, and rho d rho. So by the way, pay your attention that in this case you have no ability to rewrite this integral to product of two independent integrals, because we cannot separate variables. We have cosine of phi in region of integration here. So yeah, we cannot do it, but that's not something bad. But anyway, so let's integrate it. So in the inner integral, we have so 1 over 2 rho square with the substitutions from 2 cosine of phi to 4 cosine of phi. So what do we have? So 16 cosine square of phi minus 4 cosine square of phi. So what do we have? So 12 cosine square of phi. And now let's also simplify this integral a little bit. So as we can see that this function is even, so we can do the following stuff. We can integrate from 0 to p over 2 and multiply by 2. Then let's downgrade let's reduce the power. So we will have 6 And under the integral 1 plus cosine of 2 phi d phi, and it is simple to integrate. So phi minus not minus, plus 1 over 2 sine over 2 phi. So from 0 to p over 2. So if I substitute p over 2, and so this part always will be equal to 0, so sine of p, sine of 0, so we have 3p. So this is the final answer. So this is the area of a region. So any questions about this exercise? Okay, I guess that no questions. And now let's calculate mass over flat plate bounded by the following area. So x square plus y square is less or equal than 4, and x and y are equal, so greater or equal than 0. Actually, this is a quarter of round, so multiply it in the fourth quarter of in the first quarter of coordinate system, but let's plot it. So x is greater or equal than 0, and y is greater or equal than 0 as well. So the following plate we have. So let's calculate the mass. Let's also write down the conditions that we need. Yeah, x squared plus y square less or equal than 4. X is greater than 0, less or greater or equals than 0, and y greater or equals than 0. And the surface density is the following. So x cube, and mu from rho cosine phi and rho sine of phi will be equal rho cube by cosine cube of phi. Okay, and now it's so we see that from the graph that phi is so has values from 0 to p over 2. And then what about rho? Rho has values from 0 to 2. Okay, done with it. And now let's write the integral. Yeah, let me remind you that mass equals so the following integral, so mu from xy dx dy. So we need to integrate the density in this region. So in our case, from 0 to p over 2, d phi, and from 0 to 2 we integrate this stuff. So rho cube cosine of phi, and also don't forget to multiply it by the Jacobian. So we have the following integral. And one more example where we can split to product of independent integrals. And here is rho in power of 4. So now we can calculate this integral separately. So I1 will be equal this integral of cosine cube. So let's simplify it. Let's use differential entry technique. D sine of phi. We have the following integral. So sine of phi minus 1 over 3 sine cube of phi. And from 0 to p over 2. And actually it will be equal to 2 over 3. So sine of phi equals sine of p over 2 equals 1. So 2 over 3. So done. And then the second integral, this one. So it is even easier. So 1 over 5 rho in power of 5 with substitutions from 0 to 5. Oh, from 0 to 2. So it is equal 32 over 5. So 2 over 3, so the final result is 2 over 3 multiplied by 32 over 5, and it equals 64 over 15. And that's it. If I'm not mistaken, it was only one requirement here. Stop. We lost 6 or what? Oh no. I forgot just to change the number of the exercise. So everything is fine. So it's done. So we have done all tasks that we planned to do. Any questions about this exercise, about the whole lesson, about previous lessons? Other questions?
Sorry, I actually do have a question. You mentioned few times the Jacobian, and I don't know what that is. Could you explain this?
Okay, yeah. So how to explain? By the way, did you have such a term in the lecture or not? So so what was so polar coordinates? No?
Like I don't really remember, but I've Googled it, and it has to do with determinant or matrix. There was like a
Yeah, it is.
Jacobian matrix.
Yeah, actually, this is the matrix of first zero and first derivative. So the zero derivative is the so the initial function and first partial derivatives of this function. So yeah, we use matrix. So matrix Jacobi is important in differential calculus. And for integral calculus, so we calculate the determinant and use this determinant in transition to polar coordinates. I don't know how to explain you in a quick way because yeah, I know that on program engineering it is so it is not such detailed stuff. But maybe, yeah, let's see. You should have it in lectures, by the way. Yeah, polar coordinates. Mhm. Okay, actually, yeah, so we don't really have a lot of time to explain it for you. But yeah, so it is so like something that we have for transformation. I hope I have partially answered your question.
Yes, you did. Yes, thank you.
Maybe more questions? Okay, if you have no questions, let's finish. So have a nice day, stay safe, thank you for your attention.
Thank you for the lesson. Have a good day.
Thanks, goodbye.